We're going to engage the microphone and start blathering just in order to assure ourselves that we're miking and talking and broadcasting and everything's happy. All right, I feel like we've accomplished something already. Live and in color. Let's have a logo just for fun. "30 seconds. Be prepared for me to start talking and you to stop talking." This is hard for some of you, I know. All right, live and in color from the beautiful campus of Big Deal University, we bring you the April meeting of the Silicon Valley Fourth Interest Group. Welcome to those of you who are here in person, and welcome to those of you who are joining us on the interwebs, either in real time or tape delay. Scotch tape delay, I don't know, it involves a bottle of scotch and I'm not sure we can manage it. All right, I'm your program chairman, Kevin Appert, and if you want to communicate with SVFIG, you can go to Ask Google, when is the next SVFIG meeting, and that'll bring you to the schedule agenda page, and not May. That was the next thing I was getting to. But if you want to communicate with us, I think the first step, the easiest step, is to ask Google, when is the next SVFIG meeting? And it'll take you to our agenda page, and my email address is there, and some links to some other pages that will get you in touch with us. What do we do? What does SVFIG do? Well, we have monthly meetings, except for May. And we have an email list where we discuss mostly Forth, although certain ne'er-do-wells have pointed out that it's sometimes mostly not Forth, but they should get over that. But we try to keep it interesting at least, and you're welcome to join the mailing list. More information about that you can get by emailing my email address, and that's on the SVFIG schedule page, and we'll put you in touch with that. So what else do we do? Well, this year we do a booth at Maker Faire. So if you want to join us at Maker Faire, come to booth 69322, 69322. I think I got that right. If not, you know, you're going to be hopelessly lost and I can't do anything for you because I won't be there. But that should be interesting. There will be many interesting Forthy things to learn about at our booth. Okay, on the agenda page, there is a link to our list of exciting books that are available for sale, and you can find out more information about that stuff by following the link. Lots of Forth material from bygone era, in particular old copies of Starting Forth, the Forth Incorporated tutorial manual to the fourth computer language. Didn't we have the agenda up a minute ago? All right. Anybody got anything they care to talk about? Short topics.
Amherst Common Language Guide. So exciting that the president or somebody at Amherst decided to take it off of internet. Happily, the internet will still find this for you. Amherst Common Language Guide. When I was a lad, I read Sam Clemens' treatise on the evolution of language, where he sort of made fun of English odd spelling. Well, sort of take out the typography and add a lot of political semantics. If you can make it through the guide, you must be this drunk to make it through the guide.
All right then. So there we were. This morning I learned that they raided a Chinese Lego counterfeiter for intellectual property pirating. And apparently they seized several 100,000 pieces of counterfeit Lego, which, as I understand it, the way this works, that's one guy's collection of Lego pieces. You know, it didn't seem like very many in terms of the actual. Well, the Chinese have never been particularly noted, present company accepted, for their respect of intellectual property. I guess neither is YouTube, unless you're a conservative, apparently. Anyway, this slide that's up on the screen involves the Trident Missile various stuff. It's from the Federation of American Scientists, and they talk about various things that the military has at their disposal. But that's the nose fairing of a Trident sugarless missile, new D5 with NutraSweet. And one of the things that they did to extend the range off of the C4 was they took this thing, titanium frisbee. I don't know if it's really titanium. I don't know if it's the size of a frisbee. Well, just for fun, let's suggest that it is. And at launch, they get it up into the air. Then they light the motor. Yes, that's the way it works. They throw it up into the air from the submarine, and then they light the motor. And then it goes downrange a ways, and they stick this thing out. They crank it out. I don't know that there's an actual crank involved. They push it out on the end of this pole, and this frisbee makes the bow shock. And suddenly, magically, as if it were some baron's suspenders, the radius, the fuel mileage, if you will, increases so it can go further. How does this work? Magic. The thing, yeah. Well, it's like you push this frisbee ahead of you, and it's pulling the rest of the missile behind it. Well, are you saying that this part in here sucks? All right. Magic. That's the technical term. But I don't know anything about this. Nobody ever told me any of this stuff in a work setting, other than in a public presentation. But this is pretty cool.
torpedoes. In fact, the Russians made their torpedo, which goes, 150-mile-an-hour torpedo, by firing the torpedo and then using compressed air and putting a bubble shield around the torpedo. Reduces drag so much that it gets much higher velocity. Although it does make it noisy. Then hell, 150 miles an hour, I think it is noisy.
All right. We're going to have some schedule notes now. We believe that John Reibel, who was originally scheduled to speak on some random blathering sort of basis, is not going to be with us unless he shows up at the last minute. What's that? Well, yeah, but he said he'd be here. So who knows? Maybe he will, maybe he won't. He may not be. And Andreas has a short presentation that he'd like to give, and that'll be at that time. No. After the cake, after the break, after Dwight. So, announcements, rumors, gossip, slander, libel. All right, blank stares. That's great. Maybe. Those were the days, the olden days.
Is that it right there? That pointed frisbee on top?
That doesn't have a frisbee. It just has a point, a spike.
So they actually push the rocket out of the water with compressed air.
No, they actually have a thing called a steam generator. It's basically a rocket motor, and all it does is vaporizes a bunch of water and makes a bunch of steam. And the steam splats the thing up into the air. And you can read all about this at the FAS website. It's like, what's that? Because lighting the rocket motor underwater would be a bad idea. So everything I said about John Reibel, forget I said it.
Oh yes, fortunately avoided being hung up further on 85. Motorcycle accident there.
Oh, well, we're glad you're here.
I am too.
They were doing cleanup of the vegetation along the side of Highway 17 over the mountain, and it was stop and
Valley
go.
to the summit was stop and go.
Stop and go. Well, couldn't get over.
Dwight, are you about ready to light the fuse? All right. Why don't you mosey on up? All right. You needn't depend on the schedule to any great extent. All right. Take it and stick it, as they say.
Take me a moment here.
I feel like I should go to the bathroom with the mic on. Fortunately, I don't think it reaches that far. Clip that to your shirt.
I just got to figure out where I put my file.
Okay.
I think that's it. Ah, that's good. Maybe change the font size or something. Let's see how this is going to work. What is it? F. Got to figure out which F it is now. I don't do this all the time. I think F8. Is that right? Does that work? There it is. Up there. Yeah. The text is a little small though. Can anybody read that at all? I don't think so.
Well, I see maneuvering.
Maneuvering board problems. Okay. This was goes back to 1972. So it was at that time when things were just starting to happen. 1972, 1973. I would call that an inflection point in what was going on in the world. That was when microprocessors started to first happen. In Monterey, there's a fellow named Gary Kildall that some people kind of know. He worked for he was in the Navy, and he was at the Navy postgraduate school. He taught computer science there. He had kind of an in with people at Intel because they wanted a language they could use to build their tools on, which was PLM, called PLM. And it was interesting that he was able to get various pieces of hardware from Intel on the terms that they were, as you will see here, as he called scrap. That was his exact terms for what he was getting. I probably want to take this microphone with me, huh? It was called scrap. So he took these various things and gave them to his students to do their thesis on. Yeah. So one of the more interesting things that I saw there, I've always been kind of interested in finding old code for the 4004 microprocessor. Very, very rare to actually find working code. So I dug around on the web and found that they did two projects on the 4004 at the Monterey postgraduate school. One of them was to calculate how much weight you could put on a helicopter and safely take off, which is an interesting problem because most people don't realize that when the helicopter is close to the ground, there's a ground effect. And as soon as you get up a little higher than that, you lose that suddenly, and it loses from one side to the other, and the helicopter falls over and the blades go into the ground and you die. So it's very important to know exactly how much weight you can safely put on your helicopter based upon the density of the air and the other factors, how warm your engine is and all those kind of things. So that was one of the things that they had. The next thing they had what's called a maneuvering board problem. And I found that kind of interesting because I was in the Navy. I was never on a ship, but I was in the Navy. So thinking about ships was always kind of interesting. If you have a tanker and a destroyer buzzing along, and you want to make sure they don't run into each other, there's a problem that you have to solve. Where are they going to be at some future time, and will they collide with each other? And so you want to calculate what's called closest point of approach. And that just means that if they're going to hit, right, you can pretty much figure that. But if they're going to miss, you want to know how much you're going to miss by, so you know if you have a safety factor. Also, of course, there's the maritime rules of the road, which have to do with who you have to yield to in case one of them is required to make a maneuver to avoid collision. Surprisingly, this technology of doing this has been known since World War II, but it seems that both on the Calhoun and the Fitzgerald, somebody on the bridge did not know what they were doing and did not know how to solve these problems. Right? It's a standard kind of problem that you're required to know how to do to be on the bridge. But anyhow, this concept of closest point of approach, at the time when these guys were actually doing their thesis, Rockwell had a calculator that they used to they took an ordinary calculator and wired it up with logic to make it so it could calculate the results. They cost about $15,000 to $20,000 a piece, kind of thing, and that was what they had. So one of the students said, well, we could use like a microprocessor, a 4004. We could develop the code that would actually do the kind of operation. So that's kind of what got me started in this, right? I wanted to actually see if I could get this to work. I'm not going to go through my whole text here. You guys can read it offline. It's kind of describes what's going on. But so in the library from the Navy postgraduate school, the entire document is there for the thesis, which includes a listing in 4004 assembly code of this maneuver board calculator. So I wanted to kind of see if I can show this a little bit here. You can see the, I got to, of course, find the pointer for it again. There, it's in this one here. This is a typical page of the code. What isn't always very obvious is, like, for instance, right here, you can see right where my cursor is here, there's what looks like could be B001 or BC01 or BD01. In other words, the print quality was not exactly the best in the world. Oftentimes you can see, like here, this is a JCN. It's missing part of the character there. You can see here that this was probably a D. So transferring this into code that I could actually execute took quite a bit of effort and debugging, because especially the C's and the zeros were especially troublesome, because it does make a big difference whether it's a C or a zero. Anything that's outside of quotes, at least, is textual or just numeric. So in other words, if it's like this and it's missing the right part, and part like over here, you know it's a zero, it can't be a C, because there's no C's by themselves. But if it's got quotes around it, let's see, there's some numbers here with quotes. I just saw it a second ago, and now I don't see it. Up here, right there, there's a quote mark around that one. Those are intended to be hex numbers. So the hex numbers, of course, C's and zeros make quite a bit of difference. So a lot of my time was related to that. So I'd fiddled a little bit with 4004 stuff in the past. So I actually have a simulator that I've played with in the past for it. See if I can get it up here. Wherever it is here, where's the Sim 4? I don't see it. What did I do with it? No, of course I can't find it. Not much to show if I can't find it. I don't know what I did here. Let me reorganize stuff here, see if I can find it here someplace. Sim4 list. Should be an F file in here, but I've lost it. Anyway, it's a pretty straightforward simulator. There's the 4004 uses 8-bit an 8-bit instruction, even though the data size is 4, and it's more of a Harvard architecture rather than a von Neumann type machine. So so you just have a lookup table of 256 vectors to go through to get your execution. The simulator is pretty straightforward. It's just, runs the instruction, does whatever is necessary to create as a number of variable spaces or array spaces that you have for your things like your memory system and things of that sort, so you can tell what's going on there. But the other part that you need, if you're going to use this in a hardware configuration, is you need to have what I call the instrument file. The instrument file is where you hook it up to something, right? So there's always this side thing you have that goes with your simulator that actually makes it hook up to something. Like in this case, it was displays, a keyboard, things of that sort. In the past, I've used it also in your simulator. You have a cycle counter that you have to keep track of, so you can do things like if it's an asynchronous serial, for instance, that you're decoding with the processor, you have to know how many cycles have occurred in order for the loops and the delays and things to be meaningful. So there's another side package that I have on that, which I hope I can find. Yeah, okay, we'll try that. I don't understand where they disappeared to. That's what bothers me. They should be right there. Yeah, they're probably someplace else, or they got moved or something. Oh, here. This is where I need to be. There we go. That's probably getting a little closer. No, it's still not it. Where's my maneuver board stuff? I just recently moved some stuff off to, I wonder if I moved it rather than copied it off to the GitHub, which is entirely possible. Wow, that's weird. Let me go back one level here. Let me go to here, go to this directory. Ah, yeah, it's all here. Okay. So I'm just going to show the simple concept of a, where is it? Let me sort this now so I can find it. There we go. Okay, this is the simulator. It has a bunch of stuff. I'm using Win432 in this because my processor doesn't do 16-bit anymore. So there's some basic open and close file stuff out there, that you normally need. There's a bunch of the things that keeps tracks of the execution of the simulator. Then as we roll down here, you'll see that there is there's a thing I call the 4004 engine that actually executes an instruction step. And then there's a little further down, get to it here, through all of these various dot this, dot that. I just wanted to get, I must have, apparently I missed it. Where did it go? I'll get there just a second, read wrong. Well, I can't find it, of course. Let's just go down real quick here to this to typical instruction, right? There really is not a whole lot to it. I just create the actual instruction, what it does. Like you look at increment, for instance, which is here, which just increments a register, right? So you have to get the register, increment it, and then when I get done creating that word, I just put it in my instruction table, which is where it gets executed. I keep track of the little RRs in front of it have to do with how it's treating the registers, whether it treats them in register pairs or register direct registers or whatever. That gives a span of stuff that it can do and tells it how to make the bits for the instruction table lookup. But essentially, I just create the word and then stick it into the table, and then the table is a 256 vectors that give me my executions for the simulation. Okay, so on top of that, in order to actually debug the code, of course, I need to be able to run code in a debug sense, and this is where things look a little less clean, like normal. The fourth code you'd create for somebody, because it's right here. Oh, it doesn't want to do that right off the bat, of course. Let me go in here. Okay, you can see inside here that much of the code, some of it has some meaning. Like I have 3-letter pieces in here, like CLR is clear, TRG would be target, CPA closest point of approach, BRG bearing, RNG range, things of that sort in the code. But a lot of the execution that I do are just single letters. The reason why you want to use single letters for this kind of stuff is because you're really trying to get as much information back from the computer as you can, not give it as much information as you can possibly fill in on a line. So what we look at here, if you look at this here, you can see that when I'm actually testing out some of these pieces, right, I can create a word like test1 that will build all the information that I need to give it. So here it says it's waiting for a keyboard strobe, clear all the buffers, whatever. I'm going to the buttons for that are in the actual design would be the SPD would be the speed. So I'm telling it it's 15 knots, and I have to give it a number here. The N tells it to put that in as a number through the keyboard routine. And then decimal point says that I'm going to add a decimal point, but not put a 0 value in there. I'm going to set a course at 350 degrees with no decimal point. And then I'm going to do the DSP is a display and a carriage return, and then set that value as what's called own ship. So I'm telling it that that's my ship that I'm putting in there. So it has the vectors. Then I can put in a couple of sightings for a particular target. I call it target number 1. Give it a bearing, give it a time, give it a range. And that would be my first entry, then a second entry. And then I can display all the various results. You can see how that all comes together when I go ahead and I'll just do a okay, a bunch of warnings there for duplicate words in there. So right now I can run that test1. Oops. And you can see it prints out a bunch of numbers here at the bottom. I guess that's clear. Yeah, okay. So the first is the stuff that I entered. I entered my bearing, my speed. It's in a different order, of course. Then over here, I'm printing the time of my first sighting. I print my bearing and my range. And then the second sighting, the bearing and the range. This tells me at what time it will be at the closest point of me, what the relative bearing is here, and the range that it will be at. So I know how much that ship's going to miss me, which is very important to know. That's exactly what the captain of the ship's going to want to know. He wants to know when you're going to actually be real close to it. This last line calculates the speed of the absolute bearing and the absolute speed of that ship. This is this kind of information. This simulator, what's interesting is that the original 4004 processor was said to finish these calculations in 4.6 seconds. As you saw there when I hit the carriage return, it was a little faster than that. Now, and this is a simulation, so that'll give you an idea how fast the 4004 was. Yeah, yeah. So it's kind of interesting. So, like I said, most of the time was spent debugging the listing, not only my typos, but also those cases where I couldn't understand what letter or character that it was supposed to be in that listing was. Apparently it was done on a looked like a ASR 33. It was done on a platen that had lots of ruts in it. And because you could see that a lot of at first I thought it was a registration on the drum, the print head, but after looking at it, a lot of the missing characters were all lined up in a nice column, which meant that they probably had a platen that had been beat to death and had ruts in it that were missing the type. But you know, it was a school. They probably used what they could find. Okay, now the next part of my talk, other than to show that it actually runs, which was kind of fun, you can see here I'm in the middle of my KiCad building a board. I've just started on it, so it's not like it's gone very far. But you can see I got the rat's nest up there. I'm still laying traces and stuff like that. But it's a project in process. So that's this is going to be the see if I can point things out. This will be where the microprocessor is. These are the 4002 RAM chips that go across here. There's 9 RAMs. I'm using a slightly newer part that was mainly for the 4040 processor, the 4289 here, so I can use a standard EEPROM and standard I/O. This runs all the I/O stuff, and it up there is my diode matrix for my keyboard. At the top there are my, off the screen, are my LED 7 segments for the display. And then there's a bunch of transistor drivers there that will drive, yes, in the middle, and uses a what do you call it? 47, I think it is 47. Yeah, 7447 decoder chip for the 7 segment. The one thing that's a little bit different is I have to modify. I wanted to make the code exactly as it was originally written, but the 7 segment chips that displays that I bought have on the wrong side. So luckily, it's something you can fix in the software, because there's he tells it where to put the decimal point depending on what you're displaying on there. So it'll put the decimal point in the right place. Yeah. No, this is real hardware. This will be real hardware. This is the real stuff. Yeah. That one was given to me as a gift about 15 to 20 years ago. Yeah. Actually, I have two, but and they're both gray trace gold dot, which is the more common of the what they call zebra chips. The last time I saw one sell, it was the chip sold for $1,500. So yeah, so yeah, but it's there. I have a what they call a SIM4 board that was one of the early development systems that Intel has, and I've written software for that myself actually, because it was designed to work, where you could test your code out. You put 1702 chips in it, but it would come as a set that would have a PROM programmer board for 1702s, which take, by the way, 50 volts to program them. and so it had a PROM programmer board and had this board with code in it to take information from a teletype from punch tape that you could use to program your 1702. The only problem with that is that the code, the way that you wrote code in those days for binaries, you did what's called BPNF, and what that is you would have the letter B on your punch tape, and then you would put N or P depending on whether it was a 1 or a 0 8 times, and then you would put an F to mean that you were finished with that byte. So at 110 baud, it takes 7 minutes to download the code, or actually, excuse me, 5 minutes to download the code for a 1702, which is 256 bytes. Luckily, we've gotten better at that over the years, but I needed to replicate a bunch of EPROMs for somebody. So it only takes 2 minutes to actually do the programming of a 1702A actually. Regular 1702, it's about 20 minutes. But for a 1702A, it takes about 2 minutes to program it, because you have to allow certain time between each you can't hit it too fast, you blow it up. But so I wrote code that would replicate the EPROMs. The only tricky part with it, of course, is that I only had enough RAM for 128 bytes. So I had to do half and half and half. So I used 4 of the LEDs on it to sequence it. And then I step through where the first time it comes on, it comes up and it lights the light and lets you know. You put the master in, you hit the button, and then it goes over to where you put the copy in, you put the copy and hit the button, then you do it, you do it around and around till you, and I had to do, I did about eight copies of each code. So I've had that for a long time, and so I've had my assembler that I wrote a long time ago. It's a typical fourth type assembler, which uses RPN stuff in it. So in other words, I define the registers, and then the operation is the last part, not the other way around, like you saw in that listing. If I get back to there real quick, you could see that.
Blue screen and white.
Yeah. So there was that that I had here. Yeah. So you can see this is more typical looking listing, except for the fact that this did not use what do you call it? Most of the assemblers use position across the page. In other words, the first thing that you'd see would be an operation, and then you'd see any parameters that would go with the operation. And then these guys use this semicolon like you find in BASIC or something like that to mean that it's an extended line. Most of them do not allow you to do that. You can only put one operation per line. So when I actually wrote the code on my assembler, I actually do it an instruction per line, but I would put an indent there to indicate that this is all spread across a single line. I did it that way because then I could find the actual piece of code in the original listing faster than if I was to try to make an exact copy. But I did copy all the comments and things of that sort, so it was all pretty straightforward from that standpoint. But it's all pretty interesting. What's funny is that this particular right there, that particular one was my last bug that I located in there. Let me get it down where I can find it here. That was the last bug in my code. I thought most of these things that go in here were 0 zeros. This really is CC. and that has to do actually with the location of the decimal points is what that number is in there for. It has to do with how to calculate when to put decimal points in there. So it was kind of interesting that was the last bug that I finally got out of the code. Okay, now the other part is stuff you guys want to come around and need some place to kind of set the maneuvering board up here and show you what this actually amounts to. The way you do this manually without a microprocessor. If anybody wants to come up and watch this, this table here, yeah, and we can actually take some. Let me. Yeah. I'll just get this one out of the way. This is a typical plotting piece, exactly like the Navy would use if they manually did it. This is to the spec. There's a spec for this someplace on it. I just bought this from West Marine, so it's not like it's an official Navy thing that you can only get through the Navy. But it's kind of fun. I'm going to take some numbers off my. I'm going to take some numbers off of one of these. What you call it here? Let me get this out of the way. The text. What's interesting is the original document says in the table of contents that they have schematics, right, for this. If you go to that page, what the schematic is they show what a keyboard looks like, and they show what the display looks like. Those are their two schematics. So they were not exactly what I call a schematic, but then again, you just never know on these things. Let me go through here and just pick one of these out.
Maybe they used to have schematics.
Yeah, or something, I don't know. Okay, I'm going to write some numbers down here.
While Dwight's doing that, many of you heard this before. Many years ago, the Naval Academy used to have a required course. You figure, looking through a sextant and determining with paper and pen and maybe a laptop where the hell you were. And there would be books that would have the ephemeris and all that stuff, and you do stellar navigation. And then they came to the conclusion, that's outmoded. So it was no longer a required course, although it was still taught. Well, I think about 5 years ago, they said, wait a minute, this is a bad idea.
Really bad.
So now to this day, it's been reinstated. Several years ago, it was reinstated. Now, if you're a midshipman at the Naval Academy, you will learn stellar navigation.
What's interesting?
And that's why ship captains had patches. It was not from sword fights, but from two early sextants who would get eye burns from shooting the sun.
Yeah.
Or if you were a pirate and you wanted to swing across to the other ship and run below decks and kill everyone that wasn't a female that you could sell, you would have a patch over one eye, you'd swing across, you'd go below decks, you'd flip up your patch, and you'd have dark-enabled vision below decks.
You know, also with celestial navigation, You
Yeah.
have to do that 3 times a day.
Yeah.
You do it at just before dawn,
Yeah.
local apparent noon,
Yeah.
and just a little after sunset.
Yep.
So you can see the stars, but you also have to see the horizon.
Yeah.
And that is something you have to do.
If you want to know roughly where you are.
These war movies, World War II,
Yeah.
where a submarine had to do a local apparent noon so they could
Yeah.
know where they were. But there was a Japanese warship cruising around.
And they know you have to come up eventually.
And I guess you really want to ask yourself, how badly do I really want to know where the hell I am? I know where he is.
Well, yeah, especially when you're floating around in some of the areas around Japan where there's lots of shoals and stuff like that. It really is important to know where you are. Yeah. Yeah. This is pretty much ready here. I don't know if anybody wants to watch this up close. It's kind of interesting. Yeah. Oh, we are watching. Can we see the? I can't see it up there.
That's all right. Don't worry about it.
Yeah. Okay. Let me get this open here for a second. I have another one here if somebody else wants to try to plot as well. Yeah. I don't know why this doesn't want to open for me. I'm just coping with stuff here. I'm going to cope with this plastic box. There we go. I like to use the triangle for my right angle. Of course, I like to be able to pick it up. Yeah. Yeah, but it has a right angle on it, so that's useful. The first thing you have to do is you have to decide what scale you're going to use, because you need to know your scale factors on the side here when you plot things out. So I'm going to look at these numbers that I put here. This first set of numbers are the first sighting, and this is the second sighting that I have. This is the range in nautical yards, right? But yeah, you would use nautical yards. So anyhow, 27 is the biggest number that I have. So I have to decide which scale I'm going to use, where I can put 27 at a pretty good distance. So it looks like this first scale, the 2-to-1 scale, is the one I'm going to use for my ranges. So I'll just put range over here so I know what I'm looking at. So first thing you got to do is get your compass out, right? And so I'm going to say that my first sighting was at first I want to put my ship in here. I'm just going to draw a line for my ship, and I'm going this way. I'm not going to put how fast I'm going, but when you originally put your information down, you're putting down what they call relative information. So I'm going forward, so my course is always 0, even though I have a particular course. It's not really 0. It's 25 degrees off. The reason why you do that is because you have to do everything relative, because that's what you're taking, relative sightings. You're taking these relative sightings. So later on, when we actually figure the true course of the other ship, we'll need to rotate the vectors by the same amount, which isn't terribly hard. But I'm assuming that these numbers that I have here are the courses, are the vectors that it's going to go. So 2700, right? I would, excuse me, I picked the wrong one, actually. I got to pick one that's here. So I'll use this one, the 3-to-1. Okay, so 2700 is going to be a range of halfway about there, 2700. So 2700 and at, what's that, 340? Yeah, it was 340, I believe is what it was. So that's out here at 340. So this is my first sighting, and I put down the time that happened at 1400. And then I do another sighting at 1800, So he's clipping along. 18.8, which is right about here someplace. Okay. And that course is now at 330. So that would be over here, 330. Now it's interesting when you're plotting relative courses, if on a, because you're plotting everything relative, if he's on a straight line, you know he's going to hit you, because that's as close as you're going to get, right? So that's right. You're on a collision course, but the captain still wants to know when things are going to happen, right?
When we're gonna see.
Yeah. So anyhow, I'm going to go ahead and plot a relative course plot here, right, of this other ship. This is at 1406, right? And I can calculate the relative range now by, I just hold this on this. I'm looking for basically when his course, his relative course, is perpendicular to my ship. A beam, right here, where this is a right angle. That times, I mean that distance, or yeah, this is a distance. This distance is how far he'll be away. So I can actually, of course, take that number with my compass over here, and I can see that he's going to be a little over, looks like 9,500 yards away from me. And so that's all good to know. But now let's say I wanted to know what how fast he was going, right? And this is where I oftentimes make mistakes because I don't always get this right. Down below here, there's a calculator. I should probably use the calculator on my phone. I'm usually more accurate with that. But anyhow, so I know that he traveled in 6 minutes. He traveled this distance from this dot to this dot. So I know how much distance he traveled. I can go down to the scale here, right? And where's the distance scale? This one here. He traveled this far in 6 minutes, right? I can take the time, which is 6 minutes here, and then I can draw a line between the 6 minutes here and this line and get a speed. This, if I did this right. All right, distance, where's the speed? Down there, yeah, okay. 6 minutes, and I go through this line here. Of course, it goes off my scale, so I'll have to scale something. I'm going to scale the distance by a factor of, oh, wait a minute, I didn't go back to 0. This started at 20. Oy, there's a way to do this. I'm sorry, I'm not real good at this. I usually pull my calculator out at this point, and I forgot to bring it. So anyhow, but the other thing is distances traveled are gosh, where is the 0? There is no 0 distance.
Wait a minute, this scale right here, what's the,
Yeah,
this is the
yeah,
distance?
yeah,
I guess you're not
yeah.
concerned if it's at 0 distance you've sunk.
Yeah, this is actually, I know what I'm doing now. I just figured, yeah, this was 950, right? 950, which is actually right here on this scale.
Mhm.
And then my time was 6 minutes, which now we can do something realistic here. I plot from my 950 here to my 6 minutes there. That's much more likely. Okay, so yeah, so anyhow, this is, it says I'm doing about 4.75 knots, which is my speed here. So he's moving this way at 4.75 knots. Relative, that's correct. Now, I'm traveling at 25, or excuse me, I'm traveling at a speed of 20 knots, right? So that's over here. And it's still 6 minutes, so I have to calculate how far I've traveled. Again, I use this chart, right? I draw a line back that way, and it says I've traveled 4,000 yards during that period of time. Okay, so this guy traveled what we said this was 9.5 or 950, right? And then this way I traveled 4,000. So now I'm back to the scale thing. I have to find a scale where I need to put him and me on the same plot again. So I'm going to use a different scale for my since he's going backwards to me, right? I can plot things differently. First thing I have to do is I have to plot this. This shows you what's involved for this guy. The captain wants to know if he's going to collide with his ship, right?
But he's had practice.
Yeah, he's supposed to know how to do this. Okay, so now I have to plot my true course, which is 25 degrees. See, we'll use a longer one here. $25. Okay, it's along this line here, and I have to decide where I'm going to put my speed. I did 4,000, distance of 4,000, which is I'm going to plot with some scale here. Which one do I want to use? 4,000, 4,000. That's 4. That's got to find a nice one. This is actually the best one here because he's going to go backwards also relative to me. So I'm going to plot 4,000, right, which is out here. And now I have to take his relative angle here, which I said was 940 for the beginning, the first one, and rotate that over 25 degrees also. So that's actually going to be over here at 5 degrees, right? So I will plot now this new one. What we're going to do is calculate his true bearing and his true course, right? Okay, so I know that it was on that line, so I'm going to take that as his starting point, right? And this is how far he's traveled in the same time, but going the other way, right? Then I'm going to take that, and I'm going to I know that I have to take this and plot it as a vector. I don't know how to describe that. Yeah. I'm just gonna draw an arc here off of this, right? Then I have to transpose this, which is going to take a moment or so here. Let me do this the other way, which is where these parallels come in. If I can do this right. Yeah, I have to transpose this on top of my vector, which is right there. And let's see, am I doing that right? No, I'll do it this way. Excuse me, I'm sorry. Anyway, this is his, and he's going towards me. Is that correct? Yeah. So he has to be going this way. I'm going this way. That means that did I do that right? I always have to think about this. Yeah, I used the wrong scale. Anyhow, I have to use a smaller scale. Oftentimes I just take this value and call that the speed because everything's relative, right? So I can do that. Let me just do this. Here is his true bearing, right? And I'm at 4,000, right? So I do 4,000. Where's my scale for 4,000? This one. I have to keep track of that. 4,000. I said 4,000 yards, right? So that's not very much. 4,000 yards. 4,000 yards. And he's traveling this speed here along this path. And I'm probably getting this wrong too, so. But anyway, this is the kind of thing that the guy is actually doing for his calculation. This is the God, I still did that wrong, didn't I? Yep. I have to take this guy. That's why I have the parallels out here to do this right. I have to add this distance here that he's traveling, the relative distance here. I have to transpose that over to the tip of my position after some time, which we were going to call here. And then I have to use this to connect to this. How do I connect that now? I know there's a triangle here. I have to figure this out. Oh, I'm going this way on this one in that much time. So that's this distance here. There. Now we're getting there. Okay, so this is his vector, right? And then I have to close the vector up this way, the triangle up. That would be adding the two vectors together, and this would be his actual true course. So his true course is actually about 100 and what is that? 55 or so, 152 or 153. So his true vector is 153, and his speed is, if I can do this here, which I did from that other one. He's traveling at about a little over 8.5 knots. So okay, I finally did it correctly. I would have flunked the test because we just ran into the tanker just ran into us. But anyhow, that's essentially what the plotting is. If anybody wants to take one of these sheets home, I have extras here. I can see I put most people to sleep. But if anybody wants to take one of these sheets home to try to plot some courses and some distances, there's a web page that you can look to see how to do it. To actually how you can use one of these. If anybody wants one of these.
If you just want to get a sense of it, there's a YouTube video. There's actually a couple of them.
Yeah.
The first one that you might want to look at is linked on the agenda page. But
Anybody? Nope.
The thing about that video is that they said, oh, there's a better video at this other link. So go to that link and follow the link
to the better link. Yeah.
Or just go.
So.
Yeah, I remember this out of Dutton's navigation.
Yeah.
Book. It's about that thick.
Yeah.
I remember. I'm surprised I kept it.
Yeah. Oh yeah. 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 No, this is tricky stuff, and
but necessary, trust me.
But definitely necessary.
Yeah,
So.
a couple of years ago, the USD found that out.
Yeah.
They had 4 installations in 1 year.
Yeah. Well, they had 2 big ones. There was the Fitzgerald, and there was the Calhoun, or not the Calhoun. Excuse me. It was the McCain. Yeah. Yeah. That had the senator's dad. Yeah. Yeah. So they got hit pretty heavy for that. That was definitely an expensive operation. Well, they actually all this stuff works out on the radar screen for them, real time. All I have to do is look at it. Yeah. Yeah. Yes.
There have been cases where the folks say, "Oh, the navigation system's turned on," and it wasn't really.
Yeah. Well, that's the other thing. Sometimes they don't want people to know that they're there, but then that means that they depend on the watch that's out on the deck to actually take bearings and usually you go from like one end of the ship to the other to take relative bearings of where they are to triangulate them if you're not going to use your onboard radar. Hmm? Yeah, yeah, there's a, yes, yeah,
Actually, it's on the bridge normally.
yeah,
The port starboard watch.
yeah,
One of those, there were, I think I'm not sure which one was
yeah,
on a blog, we were discussing this.
Yeah.
When it happened, there were five people should have caught it between the two ships.
yeah,
None of them did, including the guy on the port side, port side lookout.
yep,
Who was sitting for over 10 minutes, the ship approaching,
Hmm?
and finally hitting.
oh, okay, just,
10 minutes worth of time.
okay,
Yeah, I was gonna say, they, on that, I think it was the Fitzgerald one,
yeah,
there was a 10-minute period of time where the port lookout, that's his job, he's supposed to sit on the port side of the ship and look.
yeah,
Never saw the other ship approaching, closer and closer and closer, finally it hit,
yeah,
and they still didn't report it until after it hit.
Yeah.
This was the port lookout. The navigator should also, on the radar, he should have been watching this and plotting the ship.
Sure it wasn't closed.
Yeah, yeah, that Liberian tanker.
Yeah.
And then of course, the navigator on the approaching ship should have seen the Navy ship there.
Yeah.
And again, they don't normally have as many lookouts and stuff like that, but they'll have at least one person on the bridge steering the ship, and another who is the officer who's in charge of who's responsible for if they hit anything. So he should have the incentive to do the lookouts. So there were altogether 5 people that had to all fail at the same time for that collision, and it was clear weather.
Yeah. Yeah, they were always in visual sight. So it's an interesting thing anyway. The concept of plotting these things either by hand or using the computer. There's not supposed to be anybody on the bridge that doesn't know how to do this. So unlike me, who doesn't do it every day, but it's an interesting thing. One of the more interesting drafting tools that you need is a parallel, which is what I use to move vectors around. All of the new ones, they have these little rollers. I don't know how to describe it, but the ruler always rolls parallel when it goes out back. It's a slightly different design, but this is. Oh yeah. Yeah, well, the planes are even more complicated because it got up and down as well as right and left. Yeah, so you got three dimensions to worry about. Yeah. Yeah, let me get over here with the question.
Does this system assume that you're moving in a straight line between?
Yes.
Okay, but so if you're turning during that time, it doesn't apply, right?
Right. You have to basically do your calculations based upon 3 points, and then you say, okay, this is where I think things are going to be. He's going towards me or away from me
in a straight line.
Yeah, well, not so much in a straight line. You have to kind of estimate the curvature, right? So
both ships need to be going
relatively straight. But
turning.
if you think about the fact that you have a ship that weighs umpteen tons,
yes,
right? It's much easier to just make it go in a straight line than it is to make it turn.
And the time between taking sightings is
typically the one that I had there was done at 6 minutes because it was an example, but they recommend that you take sightings every 3 minutes.
3 minutes, okay.
Right. And that way you can determine whether or not normally you're on a straight line, and the other guy hopefully is also on a straight line. If he's not on a straight line in 3 sightings, you'll know that.
Right.
Right. Yeah. And then you'll have an arc that he's following. Right. And you can actually just plot the arc with the compass if you want to see where his course is, whether he's getting closer to you or further away from you. And at some point, one of the two, like I said, there's rules of the road for being in the open ocean too. And if you're the burden vehicle, right, then you have to maneuver in such a way as to avoid being hit. I believe in the case of the Fitzgerald, the Navy ship was actually not the burden vehicle. But remember that this also requires communications between the two ships. The Fitzgerald should have contacted the other ship and told them that we're on a collision course. You know, you're the burden vehicle. Are you going to do anything? If you're not, I have to do something because I don't want to smash up, right? Yeah.
The burden vehicle, of course, is the one that has right of way.
Yeah.
But in all cases,
Yeah.
collision shall be avoided by the members of either ship
Yes.
as if necessary.
That's right.
Even though they're not burdened.
Yeah, that's actually the same thing as rules of the road for cars, right? Yeah, if you have to avoid. Yeah.
Crosswalk, if you have the right of way, some guy's barreling down at you. You want to dodge. You don't want to just stand on your rights as the party with the right of way.
Unless you're Dr. Doom, and then, you know, you
Yeah.
survive.
The same thing like
Yeah.
here on campus.
Yeah.
You get kids on bikes, they come up, you know, crosswalk,
Yeah.
straight up.
Well,
Yeah.
you're dealing with a different set of rules because you are now on the property of the independent duchy of Stanford.
Yeah.
Sub-duchy.
Well, as may be. And the kids on the bikes have no cognizance of the world outside or its rules.
Okay.
How does this relate to 4004?
Oh, because the actual code is to calculate the things that I just did on the piece of paper. The calculation that I had up there, that when I hit the carriage return it was done. that was the actual calculation of what it did. Is it did a quartic algorithm for the sine and cosine to get the sine and cosine of the coordinate, you know, the range, the x and y of the target ship. Then from those you could calculate a tangent line for the actual courses involved, and then you can do the rotations and the scaling to put them into terms of either, you know, nautical speed or true course, true range. Yeah. Yes. So, like for instance, knowing the true course of the ship, then you can plot you know, his actual course, you know, from where you saw him last, right? That he's going to be on if he does nothing. So you would know how you wanted to dodge, for instance. You'd know that. You'd be able to calculate that, you know, with the thing. There's an example that I had on the web page, which was a textual one, which has a lot of examples of how you would use the plotting here to do all kinds of things. Yeah, I believe so. Someplace it's out there. It's a it's the book. It's essentially the book that the Navy uses, and it's like page 6 or something of that, or chapter 6, and it also calculates. You'd like, for instance, use one of these boards to calculate true wind. If you had reference points, for instance, you could calculate what courses you want to set in order to make a harbor or something of that sort, and what speed you want it to run, because you can subtract off the true wind vector, things of that sort. So it shows all of these different kind of things that you do with this plotting paper. Yeah.
I thought we just make all sheets AI and then they
Oh,
themselves.
yeah, right.
Yeah.
Sorry, Dave, I can't do that.
Yeah, that would be interesting. But it's, you know, they're yeah, but there was probably an alarm went off when the other ship was approaching. That
It was
yeah.
muted.
Yeah, it probably muted. Yeah, but like I said, you know, if they plotted the points on a graph like this, like I said, when it's on a straight line to you, you're on a collision course. You just have to decide what you want to do with that. So, yeah, yeah, yeah. I always like the joke where the captain of the ship gets on the radio, and they're communicating back and forth based upon their radio ID, right? And he's telling the other guy that I'm the captain of a U.S. Navy ship, and you need to change your course and to get out of my way because I'm coming through. And finally, the other guy says, "Well, yeah, you understand we're a lighthouse, right? So it's your choice." So, so anyhow, relative.
General quarters, collision stations.
Anyhow, as far as related to Forth, the entire simulator, of course, is all written in Forth, and everything was done in Forth. Yeah.
Which will write code to emulate processors
Yeah.
and any peripherals that are connected to it.
Yeah, yeah.
I think, guys, imagine doing that for a 4004. Oh my God. Was there ever a 4040?
Yeah, there was. The 4040 had interrupt capabilities and had a secondary register set, so you could swap things out when you were doing things like the Z80. Yes, but and it had the ability to do twice as much ROM. So there were a number of features on it. The 4004 really wasn't the first microprocessor, but it was the first commercial microprocessor. TI was working on one at the same time, but they didn't have theirs working. And there was also one that was developed for, I think it was for the F-15 fighter. And it was developed about 2 or 3 years before the 4004. And that didn't come out until just about 4 or 5 years ago because it was classified. So, yeah, that's what I mean. I think it was the F-15 fighter. Yeah, because that particular fighter was one of the first unstable flying planes and needed a computer to actually keep it from going berserko in the sky. Yeah.
Wasn't the 4004 also a chipset? Yeah.
Yes. Well, yeah. Yes. Oh, okay.
Yeah. His name is Dwight.
Yeah. There you go.
There you go. Kevin.
Yeah, it has specialized ROM. No, the data function was all right. Yeah. The 4004 we did go was a physical. They also sold it in the United States. Anyhow, the microprocessor that went in it was interesting. Engineers from Japan comes over. They hadn't even hardly started the design of the 4004. It was still a conceptual piece of paper. And at the same time, they just hired from Fairchild. And he was the one who basically did all of the silicon based upon what the guy from Japan expected to do. So between the two, they essentially built the process. So it's an interesting project. Of course, Ajay went off to start his Xylon. Well, the processor it was making 71, 72, 73. 71, 72, 73. So it was during that time span. But they were they were so far behind that the guy that came down was just livid when he got over there.
Is this the processor that they built a mock-up of in discrete transistors?
They have since.
Yeah, I think they did a talk at
They've done,
the Computer History Museum. It may be on YouTube, so.
they've done two processors. One was a 4004 and the other is a 6502.
Oh, yeah.
But yeah, it's it's an interesting processor in how you access memory, for instance. If you want to access memory, you first tell it what bank of memory you're going to access, and then you do what's called a source instruction, which tells the memory itself to watch out for an instruction that could be a fetch or store, for instance, or an I/O operation. Yeah, and so it's like you have to pre-tell it where you're going to, what you're going to do. And if it's a memory location, the instruction you use to locate it in that memory will have the address as part of the instruction, or it will be part of it will be in a register actually. You tell it, I want to use this register to access that, whatever, relative. So it's kind of a goofy instruction to actually write code for. So you have to get used to that setup and execute thing. For any of the I/O operations, there's always a setup and then an execute, setup and execute, setup and execute. And, but it actually worked. Another interesting thing, which is kind of forth related, right, is if you look at forget the guy's name, the Japanese fella. He's written a paper about doing it. And if you look in the paper, you'll see almost forth-like address interpreter. So I thought that was kind of interesting. I have to look up the address for that paper, but it's worth reading because it's from a different perspective than if you were to read it from one of the Intel guys.
If you find it, either post it to the mailing list or send it to me and I'll post it.
Yeah, I'll see if I can find it.
All right.
Send it already or put it someplace, but I'll find it. Because it's interesting when you look at what he did. The only difference is instead of having a return instruction, you have a counter to count how many times you execute addresses. So in other words, each time you executed an address, you incremented the counter once. When the counter overflowed to 0, you were done doing that subroutine, and then you go off and do another straight subroutine. So it was a very forth-like interpreter that was in the 4000 code.
All right, we're going to take a short break, have some chocolate cake. A week or two ago, I got a note from LinkedIn saying Dave Jaffe was having a work anniversary. I think it's actually the anniversary of Dave Jaffe starting his LinkedIn account. I'm not sure what the heck it is. I don't think Dave actually looks at LinkedIn, but it's an excuse. There's chocolate cake.
Thank you, Kevin.
Yeah.
Hello world. Hello world. Does it work?
You don't want to hold that. You want to clip it to your shirt.
Put it up a little higher, a little higher.
You heard me say this about 800 times.
Hello world. Okay.
All right. Let's call it a win.
So.
What's your name?
Oh, I'm Andreas Wagner, and I just wanted to mention something I saw on the internet recently in the fourth, and came up in the fourth Freenode IRC channel. It was discussed there, and so as an alternative to putting Linux on a web server or web host and a LAMP stack or Node.js or whatever on top of Linux, you can use unikernels where you would just give nano VMS a binary like ELF file or ELF executable ELF file, and it's a special purpose. So you would, for cloud computing, you would use a special purpose application with only the functionality that you need in the ELF file included, and it's kind of similar to the concept of exokernels, where you have the operating system as a library instead of as a operating system, and you just link in what you need, or you just include what you need in the executable, and it has a single address space. It's an image with a single address space, and the advantage of this is that you have a small, you have a very much smaller image, and it also has a smaller attack surface because you only have the functionality only the functionality you need for your application is included, and so I think this would lend itself to using Forth for microservices together with maybe IoT, and it just sort of seems like with this cloud computing and embedded software almost comes full circle, maybe. At least I think that's what Nano VMS intends, and the Nano VMS cloud hosting infrastructure company, and they give on their website an example of running a fourth unikernel, and they give an example of putting G4th into a unikernel image and having a fourth cloud application, which almost feels like doing embedded software development on the cloud. And I thought that was pretty interesting that they actually put up an example of using Forth for unikernels, using Forth on their platform. And there's a discussion on Hacker News, and on IRC, our drop exit said that ROM kernels are something he considers even more interesting than unikernels, because it gives a way to leverage device drivers without. It's even more bare metal, I think, than unikernels. But yeah, I just thought that was interesting. That's all I've got. That's it. Any comments? It's yeah. I'm not actually all that familiar with them. Yeah. It's a yeah, I don't have a succinct description of it, but I think it doesn't require as much. It doesn't require an OS underneath.
Oh, self-contained.
Self-contained, at least, yeah.
Okay.
Okay, it's self-contained. It doesn't require like a. You seem to have a better description of it.
Yeah, it's everything that you need. You literally can like boot this up into a system, you know, and have it run. It's like think of when you boot up, say, like Linux.
Yeah.
That says, yeah, it is. It's all it's doing. A rump kernel is a really cut down version.
It's just bare metal, basically, almost.
Well, no, it runs in bare. Well, it runs in bare metal, but it gives it a really stripped down version. You know how with Linux you can get bloat and you have all this other stuff in there where your executable kernel is huge.
Yeah.
Well, this is just that's all you're going to need.
Yeah.
Okay. Yes, this is now starting to come back.
Sort of like if you're not going to be using any printer interface, there's nothing there having to do with the printer or any other peripheral around. You just load in what's going to be used for that particular application. Is that correct?
Yeah, it's just like an ELF binary that you give to Nano BMS.
This sounds like the sort of pseudo feud that's been going on between open firmware and U-boot and the initd kernel.
Yeah.
Is there are all three ways to do things. The fourth way is probably the lightest. U-boot is even heavy compared to fourth.
Yeah.
And the initd kernel is even another order of magnitude heavier, but still smaller than the full Linux kernel.
Yeah.
So you've got, at that low end, yeah, there's always been good interest in it.
Yeah. This is just interesting to see it at like the web hosting level with unikernels. It's something I hadn't seen before.
Yeah.
Yeah.
Yeah. It's interesting to see it come around again. There's been a bunch of diagnostic, or not a bunch, but a few companies that do low-level diagnostics down using fourth, and then cover up that they're using fourth.
Yeah. Yeah.
You remember I've spoken about marrying fourth with a real-time operating system?
Yeah.
Well, there's in development of that, you can get a real-time, an RTOS shell, so that you can say, okay, well, I'm going to start fourth, okay, blah, 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 blah. Well, what you can do is you can actually come up with an application that's like a rump kernel that has everything that you need and only what you need.
It's like a little turnkey that you pull out.
Yeah, yeah. In fact, it can be headless fourth for all that matter.
Yeah.
Which would, you know, someone would try to reverse engineer it to be going, what is this stuff? It's just a lot of pointer chasing. That's kind of that's a good idea there. Rump kernel is just, you know, put whatever you need and that's it.
Yeah.
It's common in a manufacturing environment where you're going to have a very, very small kernel that just does diagnostics and nothing else.
Yeah.
And that's where this is the most valuable.
Yeah.
Well, the reason why they're coming up with all these unikernels and everything, you know, when they came out with containers like Docker and stuff like that, you know, you still have to have a host operating system. You got all this complexity that can be taken advantage of by an exploit. So everything about the rump kernel is to basically make that attack vector so small that they can't use any of those resources, because the application doesn't allow you to break out of the sandbox, because the sandbox is that, and that's it. You can't actually jump past, like jump into a VMware, which last DEF CON or something like that, or where they were able to break out of the VM shell and get into, past into the host and do really nasty things.
And obscurity is your friend.
Yeah.
The more obscure it is, the more security you got.
Well, you just take everything away.
Correct. You just
take it away.
just take it away, and nobody can use it, except for the ones doing the diagnostics, or the VM, or running a Docker package.
Yeah. In this example that they gave, they put G4 in a unikernel, and that almost feels like a little too much because G4 is like an operating system. The fourth,
G4's a little bit big for that.
yeah, I would more prefer to take a turnkey of a fourth application and just extract all the words, just what I need, something like that.
I would certainly take the heads off.
Yeah. Yeah.
At the very least, take the heads off.
Maybe.
Unless you need, well, there is also the philosophy of open boot and open fork, or the open firmware. There is always a point in time where you want to, on a live machine, get down and see what's going on.
Yeah.
When you're in diagnostic mode. So in that way, you tend to keep things around, but you want it as obscure as possible.
Maybe you could have a tethered fourth where you just have the headers in the
I've never seen anybody
dictionary on your laptop, and then you have the unikernel and OpenVMS, which is headless. You just have the headers on your laptop.
Right. We would do that at 4th Inc.
Yeah.
Where we would tether and have only the headers on your development machine.
Yeah.
But it's a real complex way of doing things.
Yeah.
The add-on to that is taking the headers and having them be a file or an add-on to the kernel that has enough information just in the header part to attach correctly and be usable. So it can present a named interface at that point. And only a few people first know how to do it, and second can make use of it, because those are probably kept proprietary within the company putting the whole thing together, and they only appear in the target when it's being debugged.
Correct. Correct. That's the whole one.
That's right.
Is you want to have, in some cases, you're going to want the debugger, the technician, to enhance the system so that it can be debugged.
Right.
And nobody else can do that.
Right.
That's the whole goal.
Yeah, because if you tell them what the ports do, they can do bad things. Yeah, I do bad things anyway. I mean, what we consider bad things, obviously, I consider them essential things. But I don't write nasty words. And one kid tell me, "Oh, you could use this to write some nasty word or some sort, right?" There's no reason to do that.
People suck.
Yeah.
There's nothing out there.
The worst that can happen is spend the rest of your life in jail. And the best that can happen is that you'll destroy people's lives. And I can't imagine why you even want to try to do that.
I wouldn't try to get any pleasure out of that.
Yeah, there's a class of people that do.
Yes. But if they really understood how much damage they were doing, they probably wouldn't do it. But they just don't really grasp that. It seems kind of almost harmless.
Well, it starts with a narcissist attitude that
Yeah.
what they're doing is important.
Yeah.
And if we remember that nothing we do is important, we're better off.
That's right. Just temporary here or dust up. That's it.
That's why we're archiving.
Yes, we are. Yes, we're archiving as much, fourth documentation, literature, and
Well, through these meetings, yes, we are.
Yeah.
well, not only that, but physically too.
He's been scanning.
Yes.
Oh.
It's just like that 4004 code, right? I mentioned in that document there that I've talked to the Intel Museum, and they have nothing.
Really?
They are not a museum.
No, they're not.
No. They have nothing on
claim
4004.
to have a museum.
Yeah.
But it's,
It's
it's marketing.
Yeah, it's only marketing. It's really not a useful museum for doing research.
Right.
Yeah.
Look what we've done in the past.
Yeah. They have one 4004 processor there behind the glass.
Right.
That nobody knows what it does or what it did.
Oh, right. It's not powered at all.
Oh, no, of course not. They would never think of powering it up. Well, partly because it's just like our computer history museum doesn't power much stuff up. Most stuff are artifacts that they have. But it's not totally true because Al Kosoff is making an enormous effort to store software. He's been very, very, very busy at that. He's a software curator. And he's saying that computers without software are not computers. They're just a piece of bulky material. So, there are some of the computers they have there that will never run again, and they know that. But we're losing information faster than people realize. We call this the information age, and I always call it the information lost age because this stuff is gone. It's disappearing quickly.
No, we're creating more than we can store.
That's part of the problem. And then somebody says, well, this is obsolete, therefore we're getting rid of it.
Yes, yes.
And
nobody wants to pay for that storage.
Yeah. The other problem with Intel, since they run their own museum, is that their lawyers tell them to destroy things.
Yes.
You have this 30-day requirement from most lawyers that if it's older than 30 days, get rid of it. Destroy it.
Unless you're required to,
Unless there's a requirement.
for example, some things you have to preserve for 60 or 90 days, some things you have to preserve for 5 years, some things you have to preserve forever or as long as it's around. But Boeing and Lockheed got into some pissing contest, some lawsuit, and as part of discovery, Boeing said, okay, give us all your emails. So they handed over emails dating back 5 or 10 years or whatever. So Lockheed said back, oh, give us all your emails. And Boeing said, oh, well, we delete everything that's more than 60 days old because we can.
Yes.
And Lockheed realized, oh, why didn't we do that?
That's right. It's stupid not.
But if there's a legal action or if there's one that's imminent, you can't destroy it. And in fact, most big companies have what's called a record retention center. It is more aptly named a record destruction center. Basically, implemented in software, implemented in their administration system, there are all these boxes of documents and each one has a timer on it. And when it times out, it is practically instantaneously or as instantaneously as they can manage, those records are destroyed.
By policy rather than by a person. Person will get into trouble. A policy won't.
Well, there are people that actually shovel this stuff into a shredder on a daily basis. And, it's like that big warehouse where the Ark of the Covenant was. Raiders of the Lost Ark.
Well-
And lo and behold, there are buildings like that, or Iron Mountain or whatever, where all of this stuff is in boxes sitting on shelves in paper or microfilm or even in digital form, and each one has this meta timer.
Take back. Yeah. But it's interesting that a lot, even a short period as we're talking about since 1970, for instance, that if it wasn't for a few of us that happened to be around then, that this information would be totally lost, because the people that are coming in today, they don't understand the history of things. It's like right now, of course, AMD's at their 50th anniversary, but at their 40th anniversary, I was there, and one of the gals was going to write an article on the history of AMD, and as far as she knew, from the beginning of time, AMD made 86-based processors. I said, what? I said, you don't understand what happened even, and you don't even understand why it happened, obviously, right? Why did AMD make Intel processors? Well, they made Intel processors because the mil-spec required it. They had to have second source. And they used Intel's mask, but they used down-rev mask. So the original AMD processors had all the bugs in it that Intel had. They got sued over that, and they lost. Intel did. But the point is that that's what they were up to. They basically, you can make processors, but they'll be crappy processors. Nobody would buy them anyway. And so that's what led to AMD actually going off and design its own processors.
They even did bit slice.
Yeah.
Yeah.
And before bit slice, they did things like CRC generators, counter chips, different decoders for disk drives, all kinds of stuff. They didn't do jelly bean parts. They did what they called in those days, they call it LSI, large scale integrated, and MSI parts. But they were yes, they made the 2900 series bit slice, which was actually pretty fast for its day, but today you would consider it to be a slow processor, obviously. But it's interesting, and a lot of people don't realize those kinds of histories. It's nobody understands that Intel really wasn't a microprocessor company. They got dragged into it. And I mean dragged into it. They didn't want to be in it. They wanted to be in the memory business. Mm-hmm. They were a memory company. And the problem is that they were getting chewed alive by the Japanese, because the Japanese were shipping parts that had less than 1 ppm. And their parts had less than, maybe less than 200 ppm, if you were lucky. And they didn't understand they were getting clobbered by the Japanese. But, and Intel just basically said, well, we've got this new direction we can go. Let's stay on it for a while, see if it pays. And that's
did it?
It did. It did. It paid off. They completely dropped all their memory. But a lot of people don't realize that.
Right.
Yeah.
Right, I do remember that.
Yeah.
And they dropped full power.
Yeah.
And regret it to this day.
Yes.
They're getting their butts kicked now.
Yeah. We're AMD is very much working at low power, but the 8086.
Well, ARM's working at low power.
Yeah, but ARM will never get as good as AMD can get, or Intel.
True.
Because there's a flaw. And I was describing it earlier to him. It takes one more pipe stage to decode addresses, because when they made their 32 to 64 processor, they let some software guys decide how the instruction sets would work. And now that they've got it down on paper, they can't back it up. And it takes an extra pipe stage to decode the instructions, because of the way that you have to figure out what it is you're doing ahead of time before you can do it. And that costs you an extra pipe stage. and that's where it's going to chew them up. But it was like I was telling him earlier, there's an article I just read, it was about 2 years ago, from a university where a student had done a senior project. And they were talking about the difference in execution per watt. And they were using a stack processor. And it was running 30 times less power per watt than you could do on an ARM processor.
Oh, cool.
30 times, not 5 times.
Yeah.
That means it can be a little bit slower. If it takes twice as long to do something, it's not a big deal. It's still running 15 times better than an ARM processor. So it was an interesting article. I'll try to dig it up again and I'll give it to Kevin if I can find it.
And that's probably why TI is winning power like that.
Yeah. There's basically by just scrapping the whole concept of what they were doing. ARM, even so, RISC was made during a time when the processor was the bottleneck and the memory was not a big deal. Now it's the opposite. Anytime you have to go out to memory, it's a big hit. It's the most expensive thing you can do, and RISC does not make effective use of the bandwidth of instructions. It's clumsy, but you see that in ARM. ARM has gone with the thumb instructions now, but those thumb instructions were stuck in because they're CISC instructions, and they're put in there to reduce the memory bandwidth to speed the processor up, and it's really based upon how much you can do for memory fetch, which even like if you look at the 4004, which is what he's kind of digging into now, it ran 2 buses simultaneously and could do 3 different operations on the data and the buses all in a single instruction cycle. So that means that you can do a lot more with what you're fetching from the outside world. And you look at some of the later designs, they got better at it a little bit. It was the basic concepts. But it looks like there's a place for I think Chuck is technology-wise, he's too far behind. He's not going to be able to catch up.
We can still,
It's still,
at the 180 micron, still be 1/10 the power use of a TI.
Yeah.
And I think Chuck has the concept. He's still in a technology that is behind.
Yes.
Yeah, and did that on purpose. And I understand why he did
Because of
it.
the power trade-off. Getting smaller requires a whole bunch of other power usage for various things.
Oh, sure.
Interestingly, some of the carbon nanotube memory is copacetic with 180 micron.
Yeah.
And bringing all of the external memory accesses on chip is going to make a big difference. And we could see some very interesting things come out.
So the one thing that a lot of people don't realize is like we're 7 nanometer parts coming out now for AMD. We will be at 5 nanometers in the near future. I'm not giving away any secrets there.
Right.
We know.
But the 6T memory cell does not work at even 15 nanometers. You cannot. No, it has to do with you can't make a pass transistor that can use for read and write at the same time.
Right. Yeah. Okay.
Right. You can't do it. So even at the scales that we're doing it now, we actually have a boost amplifier to do the writes, because you have to use a pass transistor for that. But we do a what they call an 8T cell for the read. And Intel's doing that. We're doing that. Anybody that's doing small stuff is doing that. It's just the way it is. But the densities that we're getting at now, that's the other thing. A while back, I guess when we were around 190, 180 nanometers sometime, we did what we called silicon on insulator. That was to beef up the speed of the P channel transistors because of the capacitance of the large transistor. Now, even though we're doing FinFET now, and so is Intel, everybody's doing FinFET. Yeah, that boosts the gain up of the P transistor. But the problem is the transistors are not really, they're like 1/10 a factor of the speed of the part. The speed of the part is the wires. Yep. The wires are killers. Yeah, and the worst of it is we're still using routers that were basically designed 20 years ago. So that means the routers are trying to minimize the amount of silicon transistors we put on there, and not trying to minimize the wire routing. There's an enormous potential there for somebody that really understands how to do layout correctly and how to go from. The worst of it is you have to go from RTL. It's no longer from a schematic. If you went from a schematic to like a board layout, which is what I'm doing on my board. Yeah. Right. You're thinking about how many wires do I have to route over here? How many wires do I have to route over there? I'm going to place things, and that's only done at a very block level for the current processors. I know Intel does it the same way we do it. Right. You basically say, I need this much area. You get that much allocated to you. You make an estimate of how much you're going to need, and then you have the router put the parts down and lay it down. Nobody even does placement except for specialized arrays. Placement is done by an auto router, and they do a terrible job.
Is John scheduled
to
speak? Whatever. Yeah. This is interesting.
Well, I saw a
He doesn't have anything fixed. Okay. Particular. All right.
This is I'm going to ramble with whatever time is left.
I just remember I saw I'm curious what you think about this. I saw a paper where they used the parasitic capacitance between the wires in a integrated circuit to simplify the logic. Thought that was pretty interesting. Discussing with Michael.
It's possible to do that.
Yeah.
But one of the big things that they've looked at and played with a little bit, may come back into vogue, is to use they actually etch out the silicon oxide between the wires and the layers and let the wires just dangle in the air. Remember, these things are so small that at this scale, their stiffness is greater than their mass, right? So that means you can basically cantilever these wires out quite a distance, off of a via without them sagging, right? And so you actually, instead of using silicon dioxide for
an insulator, you
use
air.
Yeah. But so far, as far as I know, it's only being played with at the university level. Nobody's actually been doing it on real silicon, but I can see it happening.
I could see a manufacturing issue there.
Yeah, there's a bunch of it.
Well, does anybody see? There are various specs for chips, level. There's a particular kind of semiconductor and chip that's designed for use in artillery shells. And imagine, if you will, all of those G's when somebody lights the powder in a cannon.
There's one of the problems.
Boom!
Uranium makes a good semiconductor material. Uranium does, yeah.
But back in
better than silicon.
in World War II, one of the things that a lot of people don't realize won the war was this thing called the proximity fuse. So imagine designing a piece of electronics with tubes that survived the acceleration of an artillery piece, a gun. It's shot from guns.
And wasn't guided. It just said when it got close enough, it'll explode.
What was clever about that design is that you needed to get the shell out of the barrel before it blew up. Right. So the trick that they did is they had a little vial of sulfuric acid, and they had the plates for the battery dry. And when the shell fired, the little vial would get shattered, and the acid would flow down into the into the battery, and it was far enough away from the ship and the cannon so that it when the oscillator started, it would be away from the ship.
Yeah, that was on the later shells. The earlier shells actually used dry cell batteries. And the problem was they would be putting shells up and finding out they weren't going off when they knew they were hit very close to a target. And the batteries were 4 months old. They've been sitting in the South Pacific for all those 4 months. Yeah. In a warehouse, hot, and the batteries go bad. So they came up with the lead acid, also a thermal fuse, or a thermal battery, which was actually ignited by the ignition of the shell, firing of the shell, and it burned, heated up, and liquefied the active elements and electrolyte, and then then it became active. And it gave them the big advantage was that none of the failures that you could have in the electronics could accidentally set the shell off in the gun, because it had to be a couple of 100 yards away before the enough current build up to activate the electronics.
And you realize it was Armstrong that came up with that design. He's a very famous. Anybody knows anything about radio realizes that Armstrong mixture. The guy's name was Armstrong. I forget his first name, but he was credited with the actual successful design of the super heterodyne radio, and he was also very instrumental in various other radio designs, and also in video television stuff. He was very much involved in that as well. So it was towards the last part of his career, I guess, in World War II, because that early stuff was done in the 1920s, middle to late 1920s. The heterodyne receiver was a remarkable change. Up to that time, everything was TRF, and that was really crappy.
Oh, I remember. We take a 30-second break while John Ribble makes his way to the front of the room and grabs the microphone.
Okay.
Do you want the whiteboard or nothing? So we'll turn off the projector now.
Okay.
They like your face.
Right.
So this goes on just in your shirt pocket or something. It's on already. Given the beard, Dennis, how does that? Oh, wait a minute. Who's got, Kevin, you got the sound? Who's got? No, I've got it. No, in terms of monitoring, is that? I'm fine.
I'll check more later.
Okay.
If we interrupt you, you'll know it.
All right.
Check the stream.
That's perfect.
Yeah, that sounds good.
That sounds good. Wumpity dumpy, all that crud.
Tell us who you are.
Okay, so I guess 30 seconds is gone. I'm John Ribble, a longtime fourth person. I first came in contact with computers in 1961, 62 in a high school math honors class that met on Saturdays up at the university, where we got to use a 1620. And I wrote a little program to solve 3 equations and 3 unknowns. We had a load and go Fortran, and just 3 equations, 3 unknowns, and this little Fortran thing was too big for the load and go compiler. So we had to load the compiler tape, enter the program, punch out a paper tape, and then load that paper tape in, and then from the console enter the coordinates and
solve the equation. That paper tape I kept, and I knew nothing, and IBM in 1961-62 would release no information unless you were a customer. And so I took that paper tape and started figuring out, I didn't even know what I figured it was some kind of binary encoding, but I didn't know what it was, and started writing things down, and eventually figured out it was 1, 2, 4, and 7, not 8, and a parity bit. 5, I think it was 5. Went through 36 legal size pages of paper covered with these numbers from all of the bits in the tape. And from that, figured out the word size of the computer, and figured out, oh, here's a multiplication table, here is an addition table. I didn't know anything about how the computer was architected, didn't know anything about computers at the time. And I went in that summer after graduation from high school to IBM to see if I could get a summer job. And I took this stuff in, and the guy was amazed. He said, what, how did you figure this out? No, I'm sorry, I can't give you a manual. And I'm sorry, we don't have a job. So, IBM wasn't really happy with them. A few years later, I got a job that involved a Bendix G15 that Henry Husky over here in Santa Cruz invented, and worked on that for years. That was a drum machine that had a paper tape to load up the timing signals on the drum when you first powered it up. And fascinating working with a drum machine. And then with there's another small drum machine that I worked on where the only programmer access to the machine was the oscilloscope that was maybe three inches long, that showed 32 bits in a square wave pattern. That was the single word that you could look at a time in the machine when you wanted to try and debug. That one also, the hardware was such that if you turned the machine off, you had to wait 3 hours before you could turn it on again, because of the differential cooling of the drum material and the head material. As if it was cooling down and you turned it back on again, the drum would expand faster than the head, and it would collide before it came back up. Anyway, fun times. I first got involved with Forth in about 1976, 75, 76, somewhere in there. And I was just interested. I was working as a manager of a computer center, data processing center, because it was all punch card equipment, at a community college in Massachusetts. And I went down to Electro 76, the IEEE annual conference that alternated at that point between Boston and New York. And I had no knowledge of this stuff before, but there was a paper there, presented there by Forth Inc. And I got, oh, this is pretty interesting. Started playing around. I had, from the East Coast, gotten involved with the People's Computer Company newspaper, and I published a extensible tiny basic. Wow, a byte-coded language that you could add instructions to. Wow. And then when Silicon Valley, the Fourth Interest Group, started up, I immediately got stuff. I got Dr. Dobbs from the very beginning, when it was stapled together sheets of paper. And the first I wrote when I got involved with something called Programma Inc. in Southern California, that sent me somebody's master's thesis, but only the code part, where they had written a Forth for a 6502. And these folks were hoping that I could do it for a 6800 because I had just gotten a Sphere 6800 micro with 4K of memory and 256 bytes of PROM, which had the whole McBug kind of monitor on it. I got a Southwest Tech printer, 40 column printer. And as soon as I had something going on there, because it was so, Fourth Inc. was so enamored of the trademark, I called it SLURP, which was an acronym for Structured Language Using Reverse Polish. I call it a tongue-in-cheek acronym. And I started playing with that, and I looked at this 76 article, and then next was 1 byte and 2 or 3 cycles shorter than mine. And I couldn't figure out how it was done because there was no other information about Fourth Inc.'s code. So I've been playing catch up ever since. That was in 76, 78, somewhere in there. A friend I met, and we went to the, what was the MITSI, the processor that was the first one that came out in popular science that had the, and I can't remember the name. What? Yeah, the Altair. Yeah. MITS Altair. Yeah. We went to they had a traveling show coming through Boston. We went to the thing and got involved. But this guy ended up getting TRS-80, and he had a fourth. It turns out stolen, gotten a copy of Miller Microcomputer Services fourth. And I started looking at that and said, wow, this isn't as good as it could be. And started making suggestions and changes to Dick and Jill. First, they wondered how I'd gotten hold of a copy. But after that, I ended up buying one, I think, because I went out and got a TRS-80 just on the basis of that was a machine that Forth would run on. And because when I shown these changes to Dick and Jill, they said, oh, how'd you like to work for us? And so that was in, I think it was 78, 79, and somewhere in there I started working with them. Wrote odds and ends of code, but mostly just helped their main programmer, Tom Dowling. Oh, he was in one of these gurus. He was working at Raytheon at the time, had been working there for many years. And when he had his own personal skunkworks, where people had learned over a period of time that when they were up against a deadline and they couldn't get anything done, or couldn't figure out how to finish it, they'd take it to Tom, and over the course of a couple of days and nights and stuff, he'd come back with a whole thing working for him because he had implemented his own Forth and was doing it under the table in Forth to get all these projects done. And he, like Chuck, was not at all excited about dealing with people. He liked to write his code. And he came to work for Miller's. They were partners, and I sort of assisted. My main job was to clean up Tom's code because he would just cram. We were in blocks and just cram everything in, and mine was to straighten it out and make it so it could be maintained by mere mortals rather than the one person that had invented it, had put it all together. And with that, I came up with ideas and odds and ends of stuff. Finally, 1980 came out with Dick and Jill to first formal and presented a, what do you call it, whiteboard talk, a paper talk thing on why true should be -1 instead of +1. This was after 479, beginning 80. And I was shaking as when Chuck came by and was asking, and I gave him all the reasons I'd come up with, and said, well, you know, Dean's been telling me we should be doing this for quite a while now, and I'll have to think about it. And so 480 had it transferred over to a -1 from 479's +1, and everybody got screwed. It was so much fun. But just doing all sorts of stuff. That comes up to 80. And that was my first time I'd met Chuck, coming out. Worked on a project in the early 80s with some programmers from Miller's. They had a product that they called Forthright, which was a word processor, and it was actually a pretty reasonable word processor on the TRS-80. When the IBM, the PC came out, they immediately transferred, got everything working on both the TRS-80 and the PC. But back on the TRS-80, it was kind of interesting doing this thing. My wife was a writer, and I talked her into using it. So now we had 2 TRS-80s at home, and she went from 3x5 cards with all of her notes and stuff to using Forthright to actually do it. And she found it quite useful and kept some good feedback for changes. But with that, and then Tom started getting this idea for a spreadsheet, because 123 was out, and various other folks were doing. What was the competition for that? There was Lotus, and no, the spreadsheet one. But then what Tom came up with was a spreadsheet in which each cell could be expanded into a whole word processing document. So it had, the text could be exploded, the cell could be exploded, and you could put a whole text document in there. Or you could have formulas, and the formulas were forth, and they were compile and go. So the first time it was text formula, and the first time through it would compile it. The source code for this, what happened was it started to look pretty interesting, and an outside person, friend of somebody's, came in and yanked all of us, there were 4 or 5 of us, yanked us off into a separate company that worked on this thing and came up with a really tight document or tight product. Leo Brody wrote a manual for it, and Borland ended up buying it, which killed it, because they found that it was smaller and faster and cheaper than their low-end product, and it was actually better than their high-end project. They didn't have a place that they could put it in their product line. It just didn't fit. And so it died. Companies tend to do that. Yeah.
Because Sanders had bought Calcom, where I worked, then all of a sudden they said, well, we already have CADM.
Right. Why? Yeah.
Well, the only reason what happened was the guys that were running Calcom said, okay, we'll take it over, and it became EasyCAD. Yeah.
There was a medical imaging company called Imatron. And they were bought by a larger company that had a number of products, among them a medical imaging product that wasn't as good as Imatron.
Mm-hmm.
And basically, they supported the older Imatron machines for a while, but pretty much
manufacturing new ones because the competition was better than just bought it and repaired it. And something else happened in 80 and 81 is that Chuck got totally tired of commercial processors. They just didn't work the way he wanted them to work, and he started doing stuff on his own, making his own processor. And he put out feelers, I think it was in 82 or 83, put out feelers to folks, and the 3 or 4 of us on the East Coast got together $5,000 to send out to Glenn Hayden, who was coordinating this ECHL chip or board that was going to be a processor, ECHL Logic. Yeah, ECL. It was took a little power, but it was small. It was pretty fast. And it never got finished. Pieces never quite made it. But in that same time, Chuck met one of the first people who have ripped him off over the years, John Peers. And this is going public, so I'll probably get all kinds of libel out of it. But John caused the whole formation of this Fourth Inc. and Novix, all of that kind of stuff going on. And that was formed in 84. And I, living in Boston, 85 or 84, a couple of the other owners of a group house and I had gotten married, and okay, how can we get out? And by giving him some cash, and we got a whole year before we had to sell the house because we couldn't find other people who wanted to buy it and keep the group going. So we sold the house in the summer of 85, and Cheryl and I moved out to California and settled on Santa Cruz as a balance for her art and my computer stuff. And I'll stop with the story at that point because it's 4 o'clock. Yeah? But I came out with no job. I'd been self-employed. My first job after college and being drafted was this community college data processing director. They had tab equipment, punch card equipment, and that was in 71. And I was hired because I knew punch card equipment. I'd worked on that, and I also knew computer stuff. So they were all, oh, wow, we're going to get a computer. And well, the Commonwealth of Massachusetts, the community colleges went out to bid 3 times. The first time, all the 12 community colleges worked together, and we got an RFP out, and some of the companies answered with stacks of paper, 4 or 5 feet high, of meeting all the requirements. And wow, we picked Xerox as the main provider, and that was in would have been 72 or 73 with their Sigma series, and Honeywell, and yeah. Well, no, it was at that. No, it was no. It was the announcement after our community college had the money commitment, and we actually ordered one. And then it was on the shipping dock when they announced that they were leaving the computer business, which the politicians in the state said, "Oh, we can't be getting computers if they're gonna be obsolete." And all of the lobbying from DEC and Honeywell in Massachusetts, Data General, Massachusetts vendors. The second RFP went out and said, well, you must choose a Massachusetts vendor, the politician said, and we could not do it. Could not pick one. The third time around, they were most of the vendors were unwilling to submit very much information because it costs a lot of money to put all that paper together. But we ended up, DEC was the main instigator, and we didn't feel that there was enough support for DEC equipment that would make it worthwhile for the community colleges to use it anyway. By 75, we had a Honeywell machine in the office. And I left the job. I was done with the politics, and I had worked with a statewide committee for a year. And that was the year 72, I think, was when microcomputers, when I first realized that, oh, I could have computing at home. And so I left. I managed a small department. I was in my 20s. I had got an ulcer. I was not excited about doing anything at that level, statewide, whatever. So at home with a computer was just perfect. And we came out to California hoping that I would be able to find a job, find work. But my dream was to come out. Novix had just been started, and I was willing even to volunteer to work at Novix. When I got out here, I found out that there were no fourth programmers at Novix. None whatsoever. Chuck was up on the mountain and came down once in a while, but there was nobody in there that knew anything about fourth, and they were trying to sell a fourth chip. So they sucked me up, got working, but I wasn't getting paid. The paychecks weren't coming. My brother is a lawyer. We put together and threatened to start a lawsuit to get me being paid. Well, it turns out the company that was providing the money for Novix was a bunch of Saudis who were bringing their younger relatives, sons, cousins, and stuff over to the United States, ostensibly to learn how to install computers with their families back home. Mostly it was to sample all the other enticements of Silicon Valley and Reno and other places nearby. And so they did not want to have any kind of legal, have to expose anything of what's going on with the legal stuff, and the threat was enough to get me some money. But I stayed on as a consultant, I signed up as an employee to make sure that I was higher in the pecking order. But that was with the first Novix chip. Chuck was not interested in fixing it. There were a number of what Greg called, terminal errors with it, but Chuck was not particularly interested, and so the hardware person, Bob Murphy, and I were tasked with coming up with the 4016 or whatever it was. It was the 6016. I don't remember what the numbers were. Coming up with the next one. And there's all kinds of inside stories that go with that. But I think I will stop with that stuff. I don't really want to go on. It'll take sitting down with a bunch of people who can sort of reminisce, feedback about the stuff. Ting was all, in and out at the time with George and the trips to China, all the force stuff going on there. It was interesting. I came one time coming over to George's office and talking about working together or doing something and noticing your fourth stuff from Taiwan that included internal things from Novix. And well, how did this get here? Because we hadn't released it and had no idea. We actually did find some other stuff internal to Novix that showed up from Russia. Okay, how did they get it? We still don't know. Sayonara.
Okay, boys. It's June, right? June.
We will be back in June. We're done for the month. Next month is Maker Faire. We'll see you in June. Bye.